Welcome to Quantum Curious, and in today's lecture, I am going to present a very important concept related to the measurement of qubits. So we saw earlier that how the measurement could be performed in quantum formalism, and we saw that the projective measurement concept. So the projective measurement concept is very simple, and it is usually used in many physical realizations like calculating the any physical observable quantities like momentum, position, and we know that the projective measurement has property that it collapses the given state, and the given state is collapsed into the eigenspace of the given measurement operator. So now I'm going to present a very generalized view of the measurement, and uh, it is somewhat different from the given measurement process, the projective measurement process that we saw earlier. So we know that projective measurements, and in some cases, we do not want to, uh, we are not interested in the post measurement state, and we are only interested in the probability associated with the outcomes. So it can be uh, associated with the discrimination of the given two quantum states and attacking and modeling the attacks of the eavesdropper. So eavesdropper sometimes could implement or could employ such kind of attack that do not destroy the given quantum state, that is Alice trying to send to Alice trying to send to Bob through the quantum channel. So these attacks uh, could also be modeled through the generalized measurements. So it could be seen that consider we have two a system or composite system that is composed of two subsystems, and we want to know only the information or measurement associated with the system A, not B. So how could we comprehend or model that kind of measurement in the quantum formalism or in some kind of mathematical way? So general measurement is you can say is very suitable for these kind of measurements. Or you can think that we want to know about the measurement outcome on given quantum states, and but we do not want to perturb the quantum state that much. So in that case, we can also employ the general measurements. So general measurements are usually associated with the measurement operators, or you can say the positive operator valued measures, or usually called POVM elements, and they have properties that their sum or the set of the operators and their sum should be equal to the identity. So in that case, it is written as this. So MX is a semi-definite operator or POVM element associated with the measurement outcome X, and we have a bunch of that kind of measurement operators, and their sum should be equal to identity for them to be POVM elements. So the probability uh, of given outcome X associated with that measurement could be calculated by the bond rule. And we would see that how it is relevant or how it is similar to the cases that we have studied in the previous case for the projective measurement. So to understand this concept, consider we have a probability mixture state, and we have POVM element, and we want to know the uh, probability of outcome X in standard basis when we measure it in standard basis. So we could again calculate the trace of the given operator with the density matrix, and writing the explicit form of the POVM element, that is the measurement operator associated with that measurement. And again, solving that equation, if we write that form of the density matrix in it, we can get this form easily. So Px is the probability of that outcome. So we could see that it is quite similar to the projective measurement of some density matrix in some basis X that we have studied earlier. So it has direct correspondence to the uh, mechanism or formalism that we have studied earlier. So we could see that the POVM element formalism is quite relevant to the cases that we have studied. So again, we consider again an explicit example. So we have a pure state and it is a superposed state with a standard basis x, and the probability amplitude is alpha x. So to calculate the probability, we know that it is the square of the probability amplitude. So again, to check whether it is uh, relevant or has some correspondence in the POVM formalism. So we would first write the density matrix associated with that pure state, and this and the measurement operator, that is the POVM element associated with that measurement, could be written as this. So again, employing that formula that we have called the Born rule, in that case, uh, again writing it in that case, and writing the density matrix form, we can end up with that probability amplitude square as the probability of the outcome x. So we could see that both the results are same. So our POVM element formalism is quite relevant and valid in that case, and it gives the similar results or identical results as in the projective measurement. So you could say that the projective measurement is the special case of the general measurements. So we have seen that we can calculate the probability uh, of any outcome with the help of the POVM elements, but we have seen that we cannot calculate the post measurement state from that formalism, because it has the reason that the given semi-definite matrix, that is the POVM element, is generally the operator with the rank greater than 1. So there is you can say no unique eigenvector of that operator, or you can say it has a number of eigenvectors in that case. So we cannot associate any kind of post measurement state associated with that measurement operator. So in order to uh, solve that problem, we can introduce the cross operator. So cross operators are just a decomposition of the given POVM element. So in that case, we can calculate the post-measurement state with the help of the cross operator. So consider we have some spectral decomposition of any semi-definite operator. That is the decomposition of operator n in terms of the eigenvector and the eigenvalue. So we can take its semi-definite square root and we can write it in that form. So we know that mx is also the semi-definite operator. So we can write the given cross operator as the square root of the given POVM element. So similarly, consider we have mx as a projective operator, and we know that the square root of the projective operator is equal to the projective operator, and we could write that the cross operator is identical to the POVM element. So if we have some unitary relation between POVM element and cross operator, we can write it in that form. So you can see that there is no uh, unique way to write the cross operator if we have some POVM element. So if we have POVM element, we cannot write the given uh, uh, quite the cross operator associated with the measurement. So we we can find so there is a way to find the cross operator we if we have measurement outcome. So consider we want to know that measurement post measurement state condition on the measurement outcome X. So in that case, we can find it with the cross operators, and the formula is given as below. So here is an example that depicts the fact that the projective measurement is different from the general measurement that we have seen earlier. So consider we have some uh, state row in standard basis and we want to know the parity of that state. Also, in other words, we want to calculate the parity of the given state by measuring the state, and we want to know that how much 00 or how much 11 is present in that state. So if we have 00 and 11 state in that given state, then we can say that the we have even parity operator, or in other or otherwise we have an odd parity in the case of 01 and 10 outcome. So the probability of getting even uh, parity is given by this, and we can calculate the post measurement state associated with that outcome. So we could see that it is just a classical mixture of 00 and 11 state, and we can see that it is not the superposition superposed state, and the superposition of the given quantum state has been destroyed by the given projective measurements. So projective measurement could be realized as consider we have photon and it has polarization in the diagonal state, and it has uh, it is making the angle 45 with the horizontal. So it is in a superposed state of vertical and horizontal polarization from the point of view of the polarization filter that is aligned to the horizontal or vertical axis. So after passing through the polarization uh, filter that is associated with that is aligned along the positive of or neck or horizontal or vertical direction, the polarization the photon the polarization state of the photon would be horizontal or vertical given the axis of the polarization filter. So it has the projective measurement has destroyed the given superposition of the photon state. So this is the example of the given, or you can say the simplest of the example of the projective measurement. So it destroys the superposition or coherence of the given quantum state. So now we would see that how it is different from in the case of the generalized measurement. So if we want to calculate again the parity of the given operator. So we have a parity operator associated with the even measurement, and again we calculate the probability of even outcome, and the post measurement state could be written as this. So we would see uh, in the next slide that how uh, the given state, that is the post measurement state in the general measurement, is the superposed state, and the superposition of the state or the coherence of the state has not been destroyed by the general measurement. So consider we have EPR state, and it is the positive parity state because it had 00 and 11 superposition, and we first employ given a projective measurement uh, on that state. So the So you can calculate easily the post-measurement state in that case as the probability mixture of 0, 0, and 1, 1. And you could see that it is not a superposed state. So the superposition is lost, and we end up with the mixture, the probability mixture state of 0, 0, and 1, 1. So again, consider we have the general measurement, and we employ the general measurement uh, rule to get the post measurement state of that EPR state. So you can easily calculate that the given uh, post measurement state is again the EPR state that we have started with. So it has preserved the quantum coherence, and this is the main difference between the projective measurement or individual measurement and the generalized measurement. So uh, in cases where we want to preserve the quantum coherence of the quantum state, and we are also interested in some kind of properties of the given quantum state, we usually employ the generalized measurement as compared to the projective or individual measurements. So in today's lecture, we have covered some aspects of the general measurement and how it is different from the projective measurements that we saw earlier. And we see that in uh, many cases where uh, we only want to know the properties of some quantum state, like its parity, we usually prefer the uh, generalized measurement uh, as instead of the projective measurement, because of the preservation of the coherence of the quantum state property. So that is for today. In the next lecture, we would see that the partial trace property, or partial trace, how partial trace could be done using some basis elements, and we would see that how it is relevant to the to some application in quantum information theory.